Right, so I've got here a revision list for a final assessment in physics, and looking at this, I've got essentially two main topics, I guess. We've got, and it seems to be mixed up, which is not ideal, but we can use a little bit of highlighting to identify this. We've got forces, and then we've got waves. I think they're the. I don't think there are any others, but let's just identify them. So we've got. So when we talk about vectors, that's going to be. In fact, it's a bit too dark. I'm going to just use a. Let's use a shape of some kind. So I'll do a star by the. I'm going to color it in yellow, and they'll do a star for anything to do with forces. So that's forces, that's forces. Obviously, the forces is forces. Yeah, all this. Energy, well, kinetic energy relates to forces, so I'm going to include that as that. And then we've got waves. So for waves, I'm going to use a triangle, and I'm going to color it in pink. So these are. I'm just going to kind of generally put the area there. So it's those three there. All this down here. This is waves. Speed is forces of motion, basically. And then we've got work done, which is again it kind of related to energy and forces, but it's more commonly taught within the forces topic, which is probably why it's on this list. Now we're back to waves. And waves again, and waves again up here, down here, and and randomly just something thrown in, something on magnetic materials. That's a bit weird, I suppose. When you look at magnetism, that there's forces involved there. It's very surprising that this would be in this list. That's the wrong one. So we want a star for that. So let's get one more shape, and we'll get a square, and I'll colour that in blue. So we have one random other topic, which I don't think I would put in waves or in forces, but obviously there are. I mean, all these, we have a tendency to try to categorize things, and it helps us to understand it. But they all interlink, don't they? In the end. So what I'm going to do here is I made something on waves not so long ago for this student. So I think I'm going to focus on the forces area of things here. So we're just going to go down the list, and then we're going to see which of these areas that I've put a star by to focus on. Okay, so a vector is something which has both size, which is otherwise known as magnitude, and a direction. Okay, so the opposite of a vector is not the opposite, but the other measurement is a scalar. There are two main types of scalar. So scalars and vectors are taught together, usually. Always, really. No, well, whenever you're introducing them, you would mention scalars as well. A scalar has only magnitude. So let's just lock that image. I'll lock that one as well. So a scalar has only magnitude. So example of a scalar would be temperature. Now, actually, I will include temperature. Temperature is a scalar. I'm going to choose another one, power. Right. So we might measure power. We measure power in watts. Generally, that's the standard unit, the standard SI unit. But the general unit we use, if we get a light bulb, it will tell you how many watts it has. So you can't really say, but what direction is the power in? Wouldn't really make any sense. Power it means how quickly you're able to do work, or how quickly something is able to do work, or how quickly something is able to transfer energy from one form to another. It doesn't matter. There's no idea of what direction. That wouldn't make any sense to talk about direction. So power is a scalar. Temperature is also a scalar. You can't be hot, or you can't be 35 degrees or 45 degrees centigrade in any particular direction. It's just how hot something is or cold something is. The reason why I wanted to talk about temperature is because temperature can be negative, at least in most of the units that we use. Now, vectors are often... So vectors have a size and a direction. So, for example, velocity is probably the first one to think about, because it also begins with VE, and it's one of the first ones taught. We already know about speed. Speed is the scalar version of velocity. If you want to measure how fast something's going, you might say it's traveling 5 meters per second. Whereas, so let's get a picture of a car, and we'll say it's traveling. We'll say it's traveling 5 meters per second. That one there, yeah. Oh, cool! It's got no background. I like it when it's got no background. So we'll say, yeah, that car's traveling at. We'll look at the speedometer, and let's say for some reason it's in meters per second. Okay, hang on a second. My keyboard's playing up. So let's say the speedometer reads 5 meters per second. So yeah, that's how fast it's going. That's the speed, right? It's also the velocity, though. So what's the difference between velocity and speed? Well, if it was going the other way, the opposite direction, if it was going left, then we could say it's traveling at negative 5 meters per second. So this is when people say to me, well, how do I know which one is positive, which one is negative? Well, generally speaking, right is positive, left is negative. Obviously, if I stand the other side of the car, my right becomes your left, and so the whole idea becomes a bit confusing. So the answer to that confusion is that it doesn't matter which side is positive or which side is negative. If you're doing a bunch of maths and you're trying to identify the final velocity or the acceleration or the direction of the force or whatever it might be, you've decided at some point in the question what direction you consider to be positive. Now, if I said it's traveling 5 meters per second, the velocity is 5 meters per second, and I just write that down, then I have decided, therefore, that the forward direction, the positive direction, is to the right. So if I do a bunch of maths and I say that I find out, let's say, for example, that the acceleration is equal to negative 3 meters per second squared, the acceleration is also a vector, that will tell me the direction of that acceleration, and it means it must be going to the left. If I decided at the beginning of the question that that left is positive, then I would have to say that the velocity at the beginning was negative 5 meters per second because it's going to the right, and I would do all my maths, and I would find out that the acceleration is positive 3 meters per second. So it doesn't matter which way around you do it; the math still works. It still works. Okay. Anyway, I've spent a lot of time talking about the first one, but I think it's an important point. When a resultant force acts on an object, the object no longer accelerates, but instead travels at. Oh, sorry. Hang on. There. Okay. This. I mean, that's wrong, isn't it? When a resultant force acts on an object, the object no longer accelerates, but instead. Okay, this is a mistake. That's really bad. I'm going to write in big letters that this. I thought I was misreading it, but I'm going to say that's a mistake. Not great. If you've got a revision list that actually has something that is wrong. So what it should say is when no resultant force acts on an object, the object no longer accelerates but instead travels at constant speed. So, and this is confusing. If I had, let's say, any object, could be a car moving along, a ball rolling across the floor, a person falling, any object moving, we always think that something can only be moving if there is a force acting on it, right? So there must be a force acting on it if it's moving, surely. let's say this object, whatever it might be, it obviously looks like a ball, but I'm just drawing a circle to represent just a general object or body, as they tend to say in science. Scientists tend to call them bodies. I'm saying it's traveling at 3 meters per second. Does that mean that there's a force? Not necessarily. If there was no, we tend to think that if there's no force, then it would slow down to a stop eventually. Well, that is our experience. If we take our foot off the accelerator, our car slows down to a stop. If we stop pedaling our bike slows down to a stop. If we're rolling down a hill, that doesn't happen, but we know there is a force. There's gravity pulling us down the hill. So if I was on a flat road and I stop pedaling, I come to a stop. So it sounds like it doesn't make sense. It sounds like what's being written is correct, but that's not correct. We should say when no resultant force acts on an object. So what is this then? How do we explain this? Well, it's basically down to air resistance and friction. If a cyclist, let's take this car at the top again. So we've got a car traveling along at 5 meters per second, and it's traveling at constant speed despite the fact that the engine is moving it forward with a force. Well, that suggests that forces are required for it to move at constant speed, but there is also a resistive force, which I'm going to call R, acting against it. I should, by the way, be drawing forces from the centre of mass, but so I will do that. I just didn't want to I wasn't sure whether or not to include that to add another level of difficulty, but we should draw forces from the centre of mass when we draw force diagrams. In any case, these two, if the object is moving at constant speed, then we would be able to say that the forward acting force, is going to be equal to the resistive force in this case, and so the forces balance out, and so there's no acceleration. In other words, the resultant force, if you add them together, would be F minus R, and that would be equal to 0 in this case if they're the same. And so the resultant force is 0, and so there's no acceleration. Remember that one of Newton's laws states that F is equal to ma. So the force is equal to the, I don't know if it's on this list, not sure. The force is equal to mass times acceleration, and so therefore, and it's probably more easily understood this way, acceleration is equal to force divided by mass. So whatever, and this is the resultant force, by the way. Sorry for using these. Maybe I should use F. I'm going to say Fe, force of the engine. Okay. So this is the general form I'm using here, and this is the resultant force. The resultant force is equal to the mass times the acceleration. So the acceleration is equal to the resultant force divided by the mass. Now, if there's no resultant force, then that's going to be 0 divided by m, which doesn't really matter what m is. Acceleration is going to be 0. So no resultant force, no acceleration. Doesn't mean it stops, just means it doesn't get faster or slower. If the object was staying still, it would continue to stay still because it doesn't accelerate. And if the object was moving at whatever speed, it would continue to move at that same speed because it doesn't slow down or speed up. So the forces cause acceleration. Forces don't cause movement, they cause acceleration, which may lead to movement, but it also could lead to the opposite of movement because the acceleration could be opposing movement and therefore slow the object down. So, once again, forces cause acceleration, not movement. Well, not necessarily movement, right? Okay. Right. Distance travels equals speed times time. Well, we know that by definition, speed is how much distance is covered per time, right? So just by rearranging that formula, distance is equal to speed times time, right? The symbol for speed is the same as the symbol for velocity because they are the same thing. If you want to get a little bit outside of the syllabus, however, you could draw this to equal speed, and that means the absolute value. I'm not sure if this gets covered in GCSE maths, but essentially the absolute value of a negative number, the absolute value is equal to the magnitude of that number. So the absolute value, So it would turn any negative number, and they would end up being the same. But usually just write speed, or if they write v, sometimes they do write s, but s is not the symbol for speed. S is actually the symbol for something called displacement, which is the vector version of distance. So coming back to vectors again, here we go. Displacement is the shortest distance between two. Okay, so displacement is a vector, and so magnitude is important. So let's look at displacement then now. We've got a guy going north for 3 meters. He goes east for, let's say, 4 meters. He goes south for 3 meters, and he goes west for 4 meters. He's back home, right? Now, what is the distance he's traveled? Well, it's going to be 6, 3 plus 4 plus 3 plus 4, 6 plus 8. So the distance that he has traveled, which we can give a little d, would be, hang on a second, 14. 14. Try not to embarrass myself on video. So again, come back to this idea here, which is outside of the syllabus. We could say that distance is equal to the well. That's a bit confusing. So yeah, so there's some other distances going to be, you add them all up, right? So if I had a milometer, the milometer would be measuring distance. Whereas the displacement means how much actual distance are you from where you started? And the displacement in this case would be 0, of course. So yeah, how does it define it here? The shortest distance from the start to the end of the journey. Well, the start and the end was in the same place. The shortest distance is, well, it's going to be 0. If he didn't quite go all the way back home, maybe he just travelled 2 meters, then the shortest distance would be from here to here, and so the displacement would also be 2 meters. Really, you should be doing it. You should be recognizing the direction in the displacement. So if he's overshot it, and he's over here, and so maybe he's gone 2 meters past it, the displacement is still 2, but now you'd want to say, we want to refer to a particular direction. How far would he have to travel? No, how much? What's this overall displacement? And it would be that much time to. So if previously he's okay, I'm blabbering here a little bit. Let me get a different color to explain what I mean. Let's say in the first example he was here, so his displacement would have been whatever that is. Maybe it's 2, and now in this second example he's overshot it. So it's also the distance is 2, but now the displacement would be -2. Once again, I have I've said that right is positive. Okay. Now I'm touching upon something here though, that if right is positive and left is negative, well, what's up and down? So, well, basically we separate up and down and right and left into 2 different categories. So we could say that he went up, he went right, he went down, he went left. We can say that's positive, that's negative, and yeah. I've kind of glossed over that just to show you diagrammatically that, but I'll briefly bring it up now that when we're looking at vectors in 2 dimensions, as you can see, these first few examples were in 1 dimension. But when we look at it in 2 dimensions, we separate the perpendicular components, which are usually up and down and left and right. And then we, within those two areas, those 2 dimensions, we define one direction to be positive and the opposite direction to be negative. That's all a bit vague until you look at examples. So, but I just want to kind of, if you've been looking at examples, hopefully what I'm saying makes a bit of sense. And if you want me to go through specific questions, then send me those specific questions and I'll talk you through it. But there are lots of videos of me going through these specific questions online already. So I've just finished by going through this, through the stars. Acceleration changing velocity over time. Specifically, it should be the increase in velocity over time in one particular direction. Yeah, well, changing velocity, I guess, is fine actually. So it's velocity, not speed. In other words, if something is moving in a circle, like the moon orbiting the Earth, it is maybe moving at constant speed, but it's not moving at constant velocity because the direction is changing, so the velocity is changing, and so it's actually accelerating despite the fact it's moving at constant speed. That's a really classic exam question there. How can the moon be said to be accelerating if it's moving at constant speed? And that's the answer. The direction is changing, so the velocity is changing. If the velocity is changing, it's accelerating. Must be accelerating, of course, because it's there's a force acting on it. And as we said earlier on, if there's a force acting on something, forces cause acceleration, so it's accelerating. Once you get into A-level, we go into a bit more detail, and I have produced a video, I think, that explains this at a level that's a little bit higher than A-level as well, if those of you are interested. So displacement, yes, done that. Kinetic energy is found in objects that move. That's not a particularly complicated sentence. You would need to know the formula as well, which is kinetic energy is equal to the half. So this, people do get stuck on this formula actually. Half mv squared. What does that mean? They often say to me, do I have to half everything or do I half the mass? When you do half of 3, what that means is half times 3. Half is a number. Half is 0.5. So this just means 0.5 times m, or times the mass, times the velocity, times the velocity. And what's more, half of the mass times the velocity squared is the same as half of all of it, because it's whenever you times numbers together, for example, a times b times c, doesn't matter what order I arrange them in, and it doesn't matter whether or not I put brackets around it. It doesn't make any difference at all. They are identical. Okay, so we can use the identical symbol here, can't we? So they are identical, and they're also identical to any rearrangement of that. Let's say B, C, A, right? So you just do 0.5 multiplied by the mass. If you want, you can do half of the mass. Sometimes that makes sense. If the mass was 10 kilograms, you could just do 5 times the velocity squared. But doesn't make any difference. Yeah. Anyway, so one of the things they would like you to do is to convert. It's not in here, mind. I would have thought this is very strange list actually here to have kinetic energy but not gravitational energy. I would have thought that might be missing from this list. We've already found one mistake, and that one of the things they would like you to do, mind you, maybe this is for foundation, not sure. Anyway, is look at the conversion from kinetic energy to gravitational energy and do calculations relating to that. And so you can, or connect gravitational energy to kinetic energy. And so it is possible to calculate the final velocity of a ball falling from a particular height, because you know that, presuming there's no air resistance, because you know that we've got a certain amount of gravitational energy, that's going to be converted into kinetic energy, and with a little bit of math you can find out the final velocity. More videos on that elsewhere on my channel and in the database, and if you want me to go through an example of that, I can. I'm just wary of time here. Speed can be calculated from a distance time graph by dividing the distance by the time. That's a weird way of phrasing it. Well, you calculate the distance by the time whether you use a graph or not, don't you? So the thing that we want to be, this sentence should be talking about here is by finding the gradient of the line. So the gradient is what gives you the speed, and the gradient of a speed time graph would give you the acceleration. So it's going to be the change in the distance divided by the change in time, and that would give you the speed, which is, yes, distance divided by time, but we need to be talking, if it's going to be talking about a graph, we want to be referring to the idea of plotting of calculating a gradient. Again, I won't go into the details of that now, but there will be videos around to explain how to do that, most likely. If not, let me know. Non-contact forces, I guess this links with the thing about this. I presume this list is so specific that maybe they've designed the test already and it's very tailor-made. So maybe this idea here isn't in it. So that's why this list is so odd. I'm guessing. I guess it's a very, very clear. They've already drawn the test up. So maybe, I don't know. I know that I've heard things like that happening this year. I mean, nothing much more to say about what's been written here than what is in it. Just learn that it's iron, nickel, and steel are magnetic. What else? So I was in the middle of talking about non-contact forces. So any sort of forces that happen when there is no contact between the two things that are experiencing the force. Usually, if you want to push a block, right, then you'd have to make contact with it, and it would be pushed. Whereas things like magnetism and gravity act at a distance. There's no touching necessary. And the other one that they've not included there is the electrostatic force. So, for example, if you rub two balloons against on your head, and then you put them near to each other, they will repel one another because they've both been charged and they don't need to touch each other. So, electrostatic is the final non-contact force necessary. If you want to get really off topic here and slightly interesting, is that actually contact forces are not actually contact forces either, because when we know that everything's made out of atoms, and we know that atoms are surrounded by electrons, and when you get one surface coming closely in contact with another surface, then it's the electrons repelling one another. So is it true to say then that nothing ever touches anything? Well, it gets a bit weird, but I won't go into it right now. But there's lots of cool videos about that, probably by Vsauce and Veritasium and all sorts of channels like that. And I think I made one too. But back to the list. Work done is force times distance. If I push something and I push it a certain distance, the work is going to be force multiplied by that distance. Not much more to say there. I guess one thing I will say with work done question is that something that does sometimes come up is we think of the example of pushing a block a certain distance, and we go, okay, that's fine. The work is equal to the force times distance, and we think that's it. But then what's happening lately? Well, it's been happening for a while actually, but there's a few exam questions that catch students out, and that is they take an object that's already moving. Let's imagine this terribly drawn car, is moving already at whatever speed, and I put the brakes on, therefore applying a force in the opposite direction of F, and eventually it comes to a stop some distance later. This could be combined. This kind of question could be combined with stopping distance, of course, but it's not in the list, so it probably won't come up. And then we would say how much energy would be required to stop that car. You would use the same formula. Work done is equal to force times distance. You could also combine that with the idea of kinetic energy. How fast must the car have been moving in the first place? Well, you can whenever you are doing work, you're converting one type of energy to another. In this case, when it's got some kinetic energy, you're stopping it. So what energy are you making? You're making thermal energy. All right. So they transferred its kinetic energy to thermal energy. Right, friction. That brings us to friction nicely. Work has to be done to overcome the force of friction. Yeah, okay. Straightforward. Non-contact forces. Okay, I think weight is equal to mass times gravitational field strength. I guess briefly to understand the difference between weight and mass. Mass is how much stuff there is. So you can imagine everything's made out of atoms, and each atom is made out of protons, neutrons, and electrons. We can think of all that as stuff, as it were. And how much stuff is there? That is measured. That is what mass is. So if you so if and that mass, that amount of stuff is going to cause a force. If there's a gravitational field, it will cause a force. So if I pick up something, I pick something up and it's very heavy, then I'm going to feel a force pushing my hands down. That force is weight. So I call it symbol W. It's a force, so it's measured in newtons, right? So weight, which is measured in newtons, has the symbol W. And I can calculate weight, as it said, by mass times gravitational field strength. So if there's more mass, there's more weight, or if there's more gravity, there's more weight. I take the same object, like a 1 kilogram mass, and I take it to the moon, and I find it's easier to lift up because there's less weight, because that's what weight means. So the mass stays the same no matter where you are in the universe, providing you haven't chipped bits off, broken bits off it, or whatever. But the weight changes because the weight is a force which is a force which is constructed of the mass and the gravitational field strength, the strength of the gravitational field multiplied by how much stuff there is. And this is what do you call it? A required practical, isn't it? So this is, I won't have time to go into this one in much detail, but basically you would have done, or more likely just studied, a practical where you would, well, as it says, you're measuring the acceleration of a trolley being rolled down a ramp, a required practical activity. Well, I mean, that's what they're called in AQA, at least. They're probably called something similar in other exam boards. And they're using a light sensor, so you're using light gates to measure how fast it's going. This should be linked to a computer to monitor acceleration. So, if you want me to make a separate video on how this practical works, I can. The basics of it is that usually a card is attached to the top of this trolley, and we know the length of that card, D, and as it cuts a beam of light, then the computer records how long that beam of light was cut for, so we have a T, and then because of that we know that the car has travelled that length of the card, D, in that period of time, T, so the velocity that car was moving at would be equal to D over T. And then it measures it a second time at the bottom of the ramp, and obviously the velocity would have changed. And so then you look at the difference in the two velocities. I guess I pretty much explained it. You look at the differences between the two velocities. You do the final velocity, which is V, and we've got another symbol for initial velocity, which is U. So just to backtrack a moment, the standard symbol for velocity is V, but if we're looking at two different velocities, ending and starting velocity, or final and initial velocity, we've got V for final and U for initial velocity. So clearly the increase in velocity would be the final, take away the initial. So that would give you the increase. Then you divide it by the time, and that's a different time that I'm referring to here. This is the time it took just to cut that bit of wire, so that would be, and this time here is the time between each cuts, I suppose. So there's three times I'm referring to here. We've got one when the time that the beam of light was cut as it goes to the first light gate, which is called T1, and then the second small is the time it was cut. It takes to cut the second beam of light at the bottom of the ramp, which we can call T2, and then we've got the time it takes to actually roll from the top to the bottom, which we can just call T. So the time between each two light gates, I guess. Yeah. So, and then you'd be able to work out the acceleration. And obviously, there'll be lots of experimental methodology involved in there. So make sure you repeat it with multiple times and get an average. What you're going to do to ensure that that there's make sure it's dropped down at the right angle every time, and all these kind of things. And also, what are you actually investigating? So I've only described a dependent variable there. I didn't the acceleration, but are we going to be investigating how the height of the ramp affects acceleration? Then there it is, right? So change the height of the ramp a few more times and carry the experiment the same way. Yeah, so that's the independent variable. The control variables are any variables which could have affected the dependent variable and that we try to keep the same, try to keep constant. Okay, so hopefully that wraps all that up. So I'm going to make I'll put the video for this little mini video lesson here. And I think you should have access to my the database already. So if you come down to here, there's a link to the one on motion graphs, and you should be able to navigate your way. In fact, let me just show you. I'll just show you how to navigate your way there now. So just yeah, okay. So this is a subtopic. We know it's a subtopic because it's got a yellow P, although sometimes I forget to colour in the P's, whatever letter they are. But in any case, it's a subtopic because it says subtopics up here. I can go back to the main topic by clicking on this one here and click it again. And I've got the main topics there. So we've got 343 resources, 29 subtopics, related topics, and yeah, you can you'd be able to find everything by by navigating through there, and then whatever topic you're looking at or subtopic, you've got loads of different resources here, simulations, practice questions, simulations, channels, videos, websites, books and articles, or resource banks. So resource banks are like other banks of resources like the one you're looking at right now. Yeah, so okay, I think I'll leave it there and place the video around about here. Cheers.